All right, so this is an ALEKS topic that's called Identifying the Important Intermolecular Forces in Pure Compounds. This is a great topic because it really gets to the ideas of intermolecular forces and trying to identify them, which I think is really important. So in this problem, we're asked to sort of look at these different compounds and then choose, do they have dispersion forces, do they have dipole-dipole interactions, and do they have hydrogen bonding? Those are going to be our three main types of intermolecular forces that we're going to be sort of paying attention to. So the first thing that I should sort of mention is that all of these are always going to have dispersion forces. So it's sort of redundant, but every molecule, as long as it's got electrons, which all molecules will, they're going to have dispersion forces. So you can always check all of these boxes. Now, for the other boxes, we really need to understand what dipole-dipole interactions are, what hydrogen bonding is, and then also what the Lewis dot structures of these compounds actually look like. So for oxygen difluoride, this is what the Lewis dot structure, that I would draw looks like. And I can recognize that this is going to have a bent shape. And since it's bent, it's going to be a polar molecule. So to determine, if these things are going to be present, you really need to know, number one, how to draw a Lewis dot structure. Number two, what the molecular geometry is. And then number three, is that going to be a polar molecule or a nonpolar molecule? And that's going to be based off of the polarity of the bonds and the electronegativities of our different elements. So if you don't know any of those things, right, it's a lot that's going into this one problem. And if you don't know any of those things, then you're going to be in trouble. So the fact that this is a polar molecule tells me that we're going to have dipole-dipole interactions. So anytime we've got a polar molecule, then we'll have dipole-dipole interactions. And we're not going to have any hydrogen bonding here. And I can recognize this because, number one, we don't have any hydrogens, right? So if you don't have any hydrogens bonded to O, N, or F, you can't have hydrogen bonding. Maybe we'll go ahead and talk about hydrogen bonding real quick here. Hydrogen bonding. And I should mention, I'm going to do this example, and I'm going to do one more example after this. So hydrogen bonding interactions, the requirements are sort of what it will look like. And X equals O, N, or F. So we need to have this sort of setup, basically. We need to have X bonded to H, and then an interaction. This interaction here is our hydrogen bond force. And really, it's just a really strong sort of special case dipole-dipole interaction, right? So if I've got X bonded to H, this is going to be partially positive. This X, O, N, or F, highly electronegative is going to be partially negative. And there's going to be a strong interaction there. So in this molecule here, I don't have any hydrogens, so I can't have any hydrogen bonding. Oxygen is going to be nonpolar. It's going to be, O2, nonpolar bond, nonpolar molecule. So it's only going to have dispersion forces. Carbon tetrafluoride, again, maybe we'll fit in a Lewis dot structure down here. Carbon tetrafluoride is going to be a tetrahedral molecule, and it's going to be perfectly symmetrical, right? I'm going to leave off the lone pairs of electrons here because you don't need to watch me draw dots. But this is going to be a perfectly symmetrical, yes, these are polar bonds, but overall this is a non-polar molecule. So yes, polar bonds, but overall non-polar molecule, because it's perfectly symmetrical. So this is going to be, again, just dispersion forces, no dipole-dipole, no hydrogen bonding, because we don't have, it's not a polar molecule. We don't have any hydrogens that can interact with that. Hydrogen fluoride is HF. This is going to have both. So HF, let's draw it over here. Partially negative, partially positive. It's going to have hydrogen bonding interactions because this fluorine could interact, as this X. We could have this interaction with an HX of another hydrogen fluoride. So let's just draw this HF. This is a hydrogen bond. This would be partially positive. So that fits. So this is going to have all three. So if it has hydrogen bonding, then we can also click dipole-dipole. All right, let's do one more, a little bit more quickly. So dichlorine monoxide. So let's go ahead and start by drawing the Lewis dot structure. This is going to be bent. This is going to be polar. Pretty similar to the one we had earlier there. So let's just write bent, polar molecule. But it's not going to have any hydrogen bonding. No hydrogen, so pretty obvious there. Iodine, just dispersion. Let's go ahead and click dispersion for all of those. Methane, again, just dispersion. Nitrogen trichloride. So I'm starting by drawing the Lewis dot structure. This is going to be trigonal pyramidal. This is going to be a polar molecule. So if you don't start out by drawing the Lewis dot structure, thinking about the molecular geometry, thinking about the polarity of the molecule, you're not going to be able to do these problems basically. But since this is a polar molecule, we're going to have dipole-dipole interactions. We're not going to have any hydrogen bonding because we don't have any hydrogens. So that's it for this one. All right, hope that helps. Cheers.